Hey guys, Mr. Rysz here to help you out with the 4.1 notes. So we're going to start chapter 4 out. We'll talk about inverse variation and the reciprocal function. So big things we're going to try to get in this section is how are inverse variation and reciprocal functions related and represented. We're going to make sure you can use the inverse variation and graph translations of the reciprocal function. So just a little warm up here. We got two rectangles shown below. We got a 2x72 and a 6x24. Both of these have an area of 144 square units, and we can get that by just multiplying the length times the width. So, okay, 2 times 72 is 144, 6 times 24 is 144. So what we want to do first is, as a class, we want to go through and kind of sketch just different rectangles that would have the same area, and we're going to organize the length and width of those rectangles. So let's see, my pen's not working. Let me pause this while I get my technology. All right, guys, I'm going to just have to try my best with my mouse to draw and write as best as I can. I apologize if my handwriting is messy. Okay, but let's get this started. And if this pen just is not working right now. Okay, so a couple different rectangles we can make. I'm thinking we can make like a really long skinny one. 3 by, why am I forgetting this now? 144 divided by 3, calculator time. 4 divided by 3 is that 48. Yep, we can have a 3 by 48. I know we can divide like 144 by 9. That's not. Oh. Yeah, that's 9 and by 16. Then we can have actually a perfect square, just like I drew, a 12 by 12. Those are all different ones. So when we look at this, if we want to consider the area is always going to be 144 units, what happens to the width of the rectangle as the length increases? So if you kind of look backwards here, as the length gets longer and longer and longer, the width gets smaller and smaller. So this is called an inverse variation, because as one thing increases, the other thing decreases. Okay. All right, so let's look at these tables here and to see if these tables represent inverse variation. So we got if x is 1, y is 12, x is 2, y is 6. So almost just like our area formula that we just did there. All right, you can see all these as the x goes up, the y goes down. So an inverse variation is a relationship between two variables such that as one variable increases, the other one decreases proportionally. All right, so that's the key word. It's not just going down, but going down the same amount. So for the table to represent an inverse variation, the product x and y, so remember product means multiply, must be constant. So if we're going to find the product of each one of these, well, 1 times 12 is 12, 2 times 6 is 12, 3 times 4 is 12. So you guys can see here, you might want to make notes that, okay, every single time we multiply x times y, we got 12, we got 12, we got 12, 12, 12. Sorry again for my handwriting. It just is going to be what it is because I have to use a mouse, but all right, so now does this table represent inverse variation? So as we can see here, as this goes up, this one goes down, so it has the potential. But what we're going to do is just check to see their products. So if we multiply x times y, well, 1 times 20 is 20, 2 times 17 is 34. Okay, already off to a bad start. 3 times 14 is 42. Okay, so these are not the same thing. We could keep going here. This is 44, that's 40, that's 30. Not looking good. All right, so these products are not constant, so that table is not an inverse variation. All right, so take a second here, try to do these ones on your own. Determine if these represent inverse variations. So go ahead, pause the video, and I will show you the answer in just a second. All right, let's see if you guys got this right. So if we did x times y here, 1 times 25 and a half is 25 and a half. 2 times 12 and 0.75, that is 25 and a half. All right. 3 times 8.5, 3 times 8.5 using a calculator, 25.5. 5 times 510 is 25.5. It's looking good so far. Oh, my handwriting is not looking good so far. 4.25 times 6 is 25.5. And I would hope they'd round a jerk in the last one. 15 times 1.7 is 25.5. So this one is inverse variation. Yes. All right, now this other table here, check to see if we did the work. X times Y. All right, 6.6 times 3, is that 9.8? 19.8. All right, 5.5 times 5, I know that's not 19.8. It's 27.5. I'm just going to stop right there. We could keep filling this up, but this would be a big no. All right, so first, can we represent inverse variation? I think we can. All right, let's move on here. So the inverse variation kind of follows this formula here, where x is always equivalent to k over y. So when we have a model here, or what we can say is that the inverse variation is modeled by y equals k divided by x, where k is this constant number. The constant number just can't be 0, but it's going to be the product of x times y. So if we look at this one here, 1 times 24 is 24, 2 times 12, 24, 3 times 8 is 24. Every single one of these here is 24. So that's our constant of variation. So to solve a problem here, we can use that constant of variation, or our k value, to help find those information. So if we wanted to figure out, if we knew we had inverse variation when x is equal to 10, then y equals 3. If we want to write an equation to represent the inverse variation and then use that to find the value of y when x equals -6, we can do like such. We can use the variation equation and say, okay, y equals k over x. And we can go through and say, okay, well, y is 3, x is 10. And if we multiply by 10 over here, we get 30, which is also what we could get if we just multiply 10 times 3. So our k, or our constant of variation, is 30. What we can then do is to plug that back into the inverse variation and say, okay, y equals 30 divided by x. So if we wanted to figure out what y is when x equals -6, we just plug that in, and then we can solve, and we figure out, okay, if that's inverse variation here, when x equals -6, y's got to equal -5. All right, so let's do this next problem here together, see what we can do. All right, so we got an inverse variation, x equals 6 when y equals 1/2. So we have the equation y equals k over x. Okay, so that means y is 1/2. We don't know what k is quite yet, although we probably could figure out real easily. And x is 6, so we just plugged in y and x. So if we wanted to solve this here, we're going to have to multiply both sides by 6 to get the k by itself. And 1/2 times 6 is 3. So the inverse variation equation would be y equals, our k is 3 over x. So if we want to find the value of y when x is 15, we're going to use this equation here, but we're going to go ahead and plug in 15 for x. 3 divided by 15 does reduce as a fraction of 1/5. There's our answer. Okay, let's clear that up. All right, so we can use that with story problems as well. All right, the amount of time it takes for an ice cube to melt varies inversely to the air temperature in degrees. At 20 degrees Celsius, it takes the ice to melt 20 minutes. All right, how long would it take the ice to melt if the temperature is 30 degrees Celsius? Okay, so think of this here. We got to identify which one's x, which one's y. Typically say x is our degrees, y is the minutes. All right, so if we know that when x equals 20, the y would equal 20, we can set up our table, our y equals k divided by x. And say, okay, y is 20 minutes, k over 20 degrees Celsius. And we can solve for k by cross multiplying here. We cross that over, 20 times 20 is 400. So our constant of variation, or our k value, is 400. All right, so then we're going to say, okay, y equals 400 over x. So if we want to figure out how long it would take, or our y value, when x is 30, or 30 degrees Celsius, we're just going to plug in 30. So we got 400 divided by 30. And that does simplify to roughly, well, 40 over 3 is the fraction. But if we're going to use minutes here, I believe that is, I'm going to just use a calculator real quick, 40 divided by 3, 13.3 repeating. All right. Okay, so that's how we can use inverse variation to solve for values. Now what we're going to do is look at the graph. So if we look at just the reciprocal function, so the reciprocal function was one of the parent functions we did way back in chapter 1. The reciprocal function was just y equals 1 over x. And if we look at that equation here, we can kind of consider a couple things. We can look at the graph and realize that our domain was all real numbers except for x. If you look here, we can't have x equal to 0 because that would be just a completely irrational, non-real number there, or basically an undefined number. And our range is also y cannot equal 0. There's no way we can divide 1 by a number and to make it equal to 0. And if we look at our table of values, this is an inverse variation because as x increases, our y goes down as well. And you can see here on our graph, and we can look at Desmos too, the graph starts going down, 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 and then it jumps and keeps going down, 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 down. It keeps going down as we move from left to right. What we also know is that there are some things known as asymptotes. So as x approaches the larger numbers here, going on towards infinity, we get closer and closer to 0, but we never actually reach 0. So we could say that there is a horizontal asymptote at 0, meaning our graph will never cross the 0 mark. There's also a vertical asymptote because as we get closer and closer to the 0 on our x value, the y gets either down towards negative infinity, or if we go the other way, up towards positive infinity. So that's called a vertical asymptote. Okay, so what we want to do here is we want to graph the function and describe the domain, range, and asymptotes of that function. Now, to help you guys out, I'm going to go ahead and just open up Desmos, and this is what I would expect you guys to do. So we're going to graph y equals 10 divided by x. Okay, so if we look at this, and we're just looking at the domain and range, the domain is still, I'm just going to put D here, is that x cannot equal 0. If we look at our graph here, we have everything all the way over. All the way over. Yep. The only time it jumps is right here when x equals 0. It makes sense because we can 10 divided by 0 does not work. The range here, if we look at our y's, we can start at the bottom and go all the way up, but we never cross the middle there as well. So our range is y cannot equal 0. Sorry for my handwriting. All right, now asymptotes of the function. We have a horizontal asymptote. Let's just say HA. Now, horizontal asymptotes, we actually have to name these as an equation. And so the horizontal asymptote would be y equals 0. And I'm just going to graph that so you guys can see here. So if I go to Desmos and I say y equals 0, you can see it makes that blue line. I'm going to go through here and actually let's make this like a dotted line. So you can see, okay, we got a dotted line, and if I zoom out, it gets real close to it, but it never ends up crossing it. And it's horizontal, it goes left and right. And our vertical asymptote is still x equals 0. And we can graph that one just like how we did this. I'm just going to change this to, I click and hold to change this to dotted line. And you can see, yep, we never crossed that dotted line as well. So we can find our horizontal asymptotes and our vertical asymptotes by just looking at the domains and ranges. The domains tells us the vertical asymptotes, and the range tells us the horizontal asymptotes. Okay, so how does that relate if we have a slightly more complicated function? So if we look at a more complicated function like 1 over x minus 3 plus 2, all that does is just translates our graph over. So you can see this k number up here at the top doesn't have any effect of where our domain and ranges are, but the numbers underneath and, to the side do. All right, so if you remember here, when we go underneath or inside of the function, it moves it opposite the way that we think. So minus 3 would move it to the right 3. If we had plus 3, it'd move it to the left 3. And the number outside translates it up and down. And so we would have here plus 2, which means we have our horizontal. So we can see here our domain and range. Like so. All right. So let's look at this one here, see if we can try to figure this one out, and then we can check it on Desmos. Or in fact, if you want to pause this and see if we got this correctly. All right, go ahead, pause. Let's do this. All righty, so if I'm looking at this equation here, I can see this is a minus 2, and then this is a plus minus 4. So this is going to go to the left 2 and down 4. So let's check Desmos out here. We got g of x is equal to 1 divided by x plus 2. Yep, that moved it to the left. And then minus 4. Nope, that's an equals minus 4. Looks like it goes down 4. So our, let's see, our domain is all real numbers except x cannot equal negative 2. All right, negative 2 there. And our range is all real numbers except for x, or not x, range is y. Cannot equal negative 4. All right, so now let's name our asymptotes. The one thing that's nice about our asymptotes, we can look at our domain. So our horizontal asymptote is an x equals, but it's going to be where the range does not work. So is negative 4. All right, and so let's just double check that on Desmos too. If I type in x equals negative 4, actually, no, I had that backwards. Oh, good morning, Rysz. It is y equals, and that's because the horizontal asymptote matches up with the range, like I said. All right, try that again. Let's see if that looks nice. And this was nice about Desmos here. Y equals negative 4. There we go. I'm going to make that a dotted line so it looks like a horizontal asymptote. It's good there. And so that means our vertical asymptote, which matches up with the domain, is x equals negative 2. We're going to double check that on Desmos right now. Yep, that looks like it works there. I'm going to change the color of it, make it a dotted line. Yep, that's the vertical asymptote. Okay, so we might have learned some new vocab words there, but let's just kind of go over a couple things. So inverse variation is the relationship between two variables such that as one increases, the other one decreases proportionally. All right, and so in algebra, we use the y equals k over x. And you can see here, and we have asymptotes with 0 and 0. The reciprocal function, which is the exact same equation there, can just be translated left and right. Now that a term, or the constant of variation, doesn't really have any effect to it, what the graph does, domain and range, but those numbers there do help determine our vertical and horizontal asymptotes. All right, guys, so this wraps up 4.1. We're only spending 1 day on this, so I think you guys will be all right. Okay, good luck on the CYU. I will see you later. Have a good one.